Hello everyone, I welcome you all to this lecture. In this lecture, we are going to solve few of the numerical problems. These problems will help you to understand the concepts which I have discussed in the previous class. So let's solve the very first problem. In the very first problem, you can see it is given that consider a channel is having a bandwidth of 5 kilohertz. So 5 kilohertz, if it is given, you can consider hertz like one signal if you are converting into 1 bit. So the bandwidth we can consider as 5 kilobits per second, right? Hertz is the frequency at the rate in which the signals are being generated in the system. So you can say the bandwidth is given as 5 kbps, right? It is easy to understand. Assume that there is no noise, so noise is not given. Find out the channel capacity if encoding level of the signal is 4. So the level of signals, you can say M or L, whatever symbol you will give for the level of signals, that is given as 4, right? So you know the formula which I have discussed in the previous class. So let's look at the solution of it. The formula is when we try to calculate the channel capacity C when there is no noise on the channel, then we apply this formula, and that is channel capacity is equal to 2 multiplied by bandwidth log base 2 and the level of signals which signal is having. So here B is given like 5 kbps and level of signals are 4. So when you put these values into it, it is 2 multiplied by 5 into 10 to the power 3 bps and log base 2 4. So this 4 can be written as 2 to the power 2, and then this will come out. So it will be 2 multiplied by 2 multiplied by 5, that will give us 20, and this is actually kbps, so we are writing the kbps. So the channel capacity is 20 kbps as per the given data, right, when there is no noise. So let's solve one more problem. Consider the same thing. So the bandwidth I am considering as 5 kbps. 5 kilohertz means 5 kbps, right, as we have considered in the previous question also. There is no noise, but the signal level of signals is given as 256. So when you apply the values into the formula, so this the value of m sorry, I need to pick up the pen. So the value of m is given as 256 and the value of b is given 5 kbps. So when you fill this value, it will become 2 multiplied by 5 kbps into log base 2 256, and this 256 we can write 2 to the power 8. So this 8 will come out, and log base 2 of 2 will give you 1 only. So this 8 multiplied by this 2 multiplied by 5, it is 80, and rest of the portion is kbps. So the answer will be 80 kbps. But remember, this formula we apply when there is no noise onto the channel, right? So let's solve another problem and consider there is a noise. So channel bandwidth is given like 5 kilohertz. Find out the channel capacity if signal to noise ratio is given 10 dB. So what is signal to noise ratio? Signal to noise ratio generally we represent as divided by n, or you can say this is the power of signal we are dividing by power of noise, right? So signal to noise ratio means the ratio of the power of signal to the power of noise, that is signal to noise ratio, right? And in the previous class I have also talked about the unit of signal to noise ratio. So generally it will be given in dB, decibels, right? So what is decibels? Decibels, when we represent signal to noise ratio in, let's say, dB, I'm saying dB, then the meaning is 10 multiplied by log base 10 as divided by n. So this is the way when we represent signal to noise ratio in decibel, right? So this is actually bell, and when you multiply this thing with 10, this is decibel. So if it is given as 10, the meaning you consider like this side you are giving 10, but this side you are having 10. If you want to calculate s to n, then you can calculate like this, and this is s divided by n, like this. So when you cancel out these 10, here it will become 1, and this will be log base 10 signal to noise ratio. So if you remove this log, it will become 10 to the power 1 here, right? So this is 10 to the power 1 signal to noise ratio, right? So that means the value of s divided by n is 10, okay, when it is given in 10 dB. So just take another example. Let's say the value is given as 20 dB or 30 dB. So if it is given 20 dB, and if you want to calculate signal to noise ratio, that means you consider 20 is equal to, in terms of dB, you write it's 10 log base 10, and it is s divided by n, right? So this will become 2 here, and when you remove this log base 10, it will become 10 to the power 2 s divided by n. So that means s divided by n, or you can say signal to noise ratio, is 100, right? If the power of signal is more and the power of noise is less, this value we will get more than 1. And if we are having very large value signal to noise ratio, that means it is a good situation when the signal is having more strength than the noise. But if this value is less, then there is a problem. Okay, so let's solve this problem. Now in this problem, the bandwidth is already given like 5 kbps. Signal to noise ratio is 10 dB. So if it is 10 dB, you can solve like this. You need to calculate s by n. So s by n, as I have already told you, it will be 10 only. Now if you apply the formula when the channel is noisy, as I have talked in the previous class, so you apply this formula. The channel capacity is equal to bandwidth multiplied by log base 2, right? 1 plus s divided by n. Okay, so when you put this value, then you are having this 5 kbps. B, the value of b is 5 kbps because it is given 5 hertz, 5k hertz, right? And this s divided by n we have already calculated as 10, so this will become 11 log base 2, right? And the value of 11 log base 2 is 3.4594. So when you put this value into it, we will get the channel capacity in kbps. So that is 17.2970 kbps, right? So I hope this is not very difficult to understand. Let's move on to the next problem. Now next problem is based on the Manchester and differential Manchester encoding. Now let me quickly revise that. In Manchester encoding, when we represent the bits, so in the middle of the period of the signal or bit period, we say in the middle, if there is a transition from low level to high level, in Manchester we say it is 1. Okay, according to IEEE 802.3, right? And if in the middle of period or bit period, if the transition is happening from high to low, that means it is representing 0. This is Manchester. In differential Manchester, there is a difference. When there is a bit period, in the beginning, whatever the, if low level is coming, let's say previously it is low, and in the next bit period, if we are going to represent 1, this low will continue till the middle of the period, and then it will deflect. So if it was low, then it will become high, right? But in case we are getting low and we want to represent 0 in the next bit period, here 0, then it will change the level in the beginning of the bit period. So from 0 to high it will become, and in the middle of the bit period also, again the level will be changed from high to low, right? So with this we can convert this thing. So let me erase it, and then we convert and represent the waveform for Manchester and differential Manchester encoding, right? So let's take it. Now if I extend these bit periods like this, so we are having these bit periods. We need to convert this bit pattern into signals as per the Manchester and differential Manchester encoding, right? Okay, so let's draw the signal as per the Manchester. So let's say I'm considering this is Manchester encoding. So we are going to represent 1, and initially we are considering the level as 0. So let's say 0 is here. Now when we want to represent 1 in Manchester, there is a deflection from low to high in the middle of the bit period. So here in the middle, there is a deflection from low to high. Now here, because we are going to represent 0, in 0 there has to be reflection from high to low in the middle. So from high level to low level, like this. Now here we are again having 0, so there has to be in the middle high to low deflection, right, in Manchester. So it should be like this, right? And here we are going to represent 1, because it is 1, it should be converted from low to high. So it will go like this, right? Here it is 1, so in this bit period also it will be low to high only, like this. Here it is 1, so again it will be low to high conversion, like this. Again it is 1, so it is again in the middle of the bit period, transmission from low level to high level. Again there is 1, so again it will be like this, 0 to low level to high level. But now here it is 0, so in 0 we need to, in the bit period, middle of the bit period, we convert from low to high. This will also have the transition from low to high in the middle of the bit period, so it will look like this. This will also have this, so it will look like this. This is 1, so 1 means low to high, and 0 means high to low, like this. And this is 0, that means high to low, like this. And this is 0, that means high level to low level conversion will be reflected in the middle of bit period, like this. And this is 1, so it will be low to high, like this. So this is the representation of these bits as per the Manchester. Now if it is differential Manchester, so in differential Manchester, let's say we are having low level initially. Now because we are representing 1, this level will not deflect till the middle of the bit period. So if it is coming low, it will become high here, like this. Okay, if initially we got high, then it will become low in the middle of the bit period in differential Manchester, right? Now here, because we are representing 0, so in 0 there will be two deflections, in the beginning of the bit period and in the middle of the bit period. So in the beginning of the bit period, from high to low it will become, and in the middle again low to high it will be converted like this. Now again we are having 0, so there will be two deflection in the beginning of the bit period and in the middle of the bit period. In the beginning, high to low, and again in the middle it will become low to high like this. Now in this period we are representing 1, so the level will not change in the beginning of the bit period, but it will reflect in the middle, so like this. Now again we are representing 1, so in the beginning of the bit period there will not be any change of the level. We will continue with low level till the middle of the bit period, and then we will change it to high. Same thing will happen here, we will not change the level till the middle of the bit period, and then we will update it like this. We will change it to low. Now again, because it is 1, so it will continue till the middle of bit period, and then it will change low to high like this. And again here, high will continue till this, and it will go low, and then it will continue. Now we are representing 0 here, so the level will change in the beginning of the bit period as well as in the middle of the bit period, right? Again 0, that means in the beginning of the bit period it will change. So in the beginning it was low, so it will become low to high, and again it will change in the middle, so high to low. Again same thing, it will be changing from low to high in the beginning as well as in the middle, high to low. This is 1, so in the beginning of the bit period it will not change, it will be low only, but in the middle it will change like this. In 0, in the beginning it will change from high to low, and in the middle low to high. Again it is 0, so it will change here, high to low, and then low to high. Again it is 0, so it will change in the beginning as well as in the middle like this. And now it is 1, so in the beginning it will not change, but in the middle it will change like this. So this is the Manchester encoding and differential Manchester encoding, right? So thank you everyone for connecting. I hope with the help of these examples you will have the better understanding of channel capacity calculation, signal to noise ratio, Manchester encoding, and differential Manchester encoding. Thank you for connecting.